So now we're going to look at enthalpy changes. So this is again the total value of the energy of a system when it's at constant pressure. So this is your energy of your system. So we're going to look at the three main processes. We're going to look at physical changes, chemical changes, and nuclear changes in terms of enthalpy and how they compare to each other. So physical. In particular, we're going to look at two. What happens when you dissolve a solid in water, and for phase changes, when you change from a solid to a liquid to a gas. So a change of state. So it's important that you remember, it's important to remember that in a physical change, there's no new substance being formed. So just the conditions of the substance changes. So if you dissolve, let's say solid sodium chloride, if you dissolve it, it's still sodium chloride, it's just mixed in with water. So if you drive off all the water, if you heat off all the water, you're left with sodium chloride still. You have ice, solid H2O, and you heat it, and it melts and it becomes H2O liquid. So the first example here with sodium chloride is an example of dissolving. And then the second one is with the ice is an example of phase change. You're changing the state of a compound. You are not changing the actual compound's chemical properties, you're just changing its physical properties. Okay, so dissolving. We call this the enthalpy of solution. So we have a change, the delta part, change in enthalpy, and it is given a subscript to indicate what type of change is happening. So this is dissolving, so it's called solution. So there's 3 steps involved in dissolving any solid, and the net result, the sum of those changes, is the molar enthalpy of solution. So basically what you have to do first is you break the forces of attraction between the solute particles, and you have to break the forces of attraction between the solvent particles. And these are endothermic changes. They are positive delta H's. And then the third step that's involved is we form attractions between the solute particles and the solvent particles in the mixing, and that part is negative. Your delta H is negative, it is exothermic. And you add these two positives and this negative change in energy, and you get this enthalpy of solution. Overall, it could be endothermic or exothermic. It just depends on the substances involved, whether or not it's going to get cold to the touch. Your beaker will get cold to the touch. That means it was endothermic. Heat went into the system. Or it's going to be exothermic. The surroundings heated up and energy went out of the system. I'm going to draw some potential energy diagrams. And a potential energy diagram shows how the enthalpy changed during the change, the physical change, in which case here is dissolving. sorry. So potential energy diagrams show the potential energy on the y-axis and time or reaction progress. You can use either one of these. Reaction progress on the bottom. And then what you have is you have the stored energy in your reactants. You would actually put in the chemical formulas for your reactants, and you have the stored potential energy for your products. If the reaction is exothermic, you will have less stored energy in your products. And that is because energy was released to the surroundings. So the difference in height between your reactants and your products for both endo and exo is the change in enthalpy for your reaction. So this height, this vertical component, is our enthalpy change for the reactant. So this one is exothermic, dissolving. And then endothermic, potential energy, reaction progress. In this case, your reactants had a certain potential energy, but the products had more stored potential energy. And what that means is energy went into your system, and that energy came from the surroundings. So the temperature of your surroundings decreased, and your enthalpy change, in this case the enthalpy change for solution, increases. So you've got here this one, our delta H is negative. Energy is released from the system. And in this case, energy is put into the system. So the enthalpy change is endothermic or positive. I like to compare this to going up or downstairs. When I go downstairs, it's a lot easier. I have to work a little bit harder to go upstairs, so I'm putting energy in. So to me, this is going upstairs. I'm putting energy, more energy into going upstairs than I am when I go downstairs. All right, phase changes. So this is changes in the state of our substance. So if we look at the diagram here, we've got solid, liquid, and a gas. And the process to go from a solid to a liquid is melting. Going from a liquid to a gas is evaporation. The opposite process, gas to liquid, liquid to solid, are called freezing and, let's see if I can pull that up, condensation. So there's one extra step that's not shown here, and that is going from a solid to a gas, and that is sublimation. And it also occurs on the other side, going from a gas to a solid, and that is also called sublimation. So this is change of states. So we will have changes in enthalpy for each state. So the process of going from one to another. And they will also have subscripts. It will be called delta HX, where X is your change. So we have enthalpy change for melting, molar enthalpy change of vaporization or evaporation, enthalpy change of condensation, enthalpy change of freezing, and we could also have an enthalpy change for sublimation. Now, this superscript 0 means that the enthalpy change is at standard atmospheric pressure, right? Because enthalpy will be different at different pressures. So this means either SATP, standard atmospheric temperature and pressure, which is 25 degrees Celsius and 100 kilopascals, or at STP, standard temperature and pressure, which is 0 degrees Celsius and 101.325 kilopascals. So if your enthalpy change is found at either one of those two temperature and pressures, we say that it's at standard temperature and pressure, or standard atmospheric temperature and pressure. So another thing to know here is that the opposite process is equal in magnitude but opposite in sign. So for a substance, the change in energy for melting will be exactly the same for the enthalpy change or energy change for freezing or for solidification. The only difference is the difference in sign. If you look at this diagram, you can see that on the top diagram, these red arrows all indicate that energy has to go in. You have to heat ice to melt it. You have to heat water to evaporate it. So on the top, these processes are endothermic. Heat has to go in. And these processes at the bottom are exothermic. Energy is released. So these will release heat, and the top will absorb heat. Now back to this opposite process, opposite sign, but same magnitude. So the enthalpy change for the melting of ice, so delta H melting, is 601 kilojoules per mole of H2O melting. So 6.01 kilojoules per mole. Freezing then is negative 6.01 kilojoules per mole. So the magnitude of the energy change is the same, just the opposite process means they are opposite signs. So when you release energy, your sign is negative, and then the quantity for melting is the same value, but it's going to be positive. So we're going to be using these later when we talk about molar enthalpies. Just in case you were curious, the enthalpy change for vaporization or evaporating is 40.7 kilojoules per mole. It takes energy to vaporize a liquid, and the energy released when that same quantity of gas condenses into a liquid, 40.7 kilojoules per mole of energy is released. Chemical changes is the next process we're going to take a look at. The enthalpy change for a chemical change is much larger than the enthalpy change for a physical change. And this is because a reaction actually occurs. And so we have delta HR, subscript R, meaning enthalpy of reaction. So this is the enthalpy change of the reaction with respect to your products and reactants. So in this equation, we have 2 molecules of hydrogen peroxide, and they are decomposing into 2 molecules of water and oxygen gas. The enthalpy change for this reaction is negative 196.4 kilojoules. So what this quantity means is there is 196.4 kilojoules of energy released in this reaction. But you have to pay attention to the coefficients. So it's for 2 molecules of hydrogen peroxide decomposing. So we can rewrite this statement depending on which reactant or product we want to talk about. So if we talk about moles of oxygen, the coefficient here is 1. So for every mole of oxygen produced, this reaction releases 196.4 kilojoules of energy. The sign did not change. It is still exothermic. And now if we look at moles of peroxide used, if we're looking at every mole of peroxide, so here we have a coefficient of 2. So if 2 moles of hydrogen peroxide produce 196.4, and this is for every 2 moles of H2O2, then if you take those numbers and divide, 98.2 kilojoules of energy is released per mole, per 1 mole of H2O2. So that would look like 98.2 kilojoules per mole, per 1 mole of H2O2. And because it's released, we would say delta H for hydrogen peroxide is 98.2 kilojoules per mole. For water has a coefficient of 2 in front of it. So for every 1 molecule of water that's produced, 98.2 kilojoules of energy is released also. So we are going to be looking at how to write chemical equations soon with the energy term in with it, and that becomes a thermochemical equation. So that's chemical. What I need you to know just right now is that much larger enthalpy change for this type of process. Nuclear changes. This is the most energy change involved in out of the three processes. So for decay, an atom's nucleus will emit particles and become an atom with a smaller nuclei, and the missing mass is converted to energy. So this is called nuclear decay. So it naturally happens. The missing mass converts to energy. We also have nuclear fission. So this is where we collide a neutron particle with an unstable element like uranium-235, and we end up splitting it into smaller nuclei, smaller elements. And for uranium-235, it emits 1.92 times 10 to the 10 kilojoules per mole. That's a large amount of energy, a very large amount of energy. The opposite of fission is fusion, and this involves the joining of two smaller nuclei. This also releases energy. This is what happens in the sun, our star. And it releases about 1.7 times 10 to the 9 kilojoules of energy per mole. So right now there's a push amongst scientists to develop the process of fusion. We can do fission at the moment, but fusion has a couple of benefits. It's the mass of 1 mole of hydrogen is a lot less than the mass of 1 mole of uranium. And the product of nuclear fission is nuclear waste, which is radioactive, while the product of nuclear fusion is helium, and it's not radioactive. Both are incredibly expensive to set up at start. Okay, enthalpy is considered to be a state function, which means it's path independent. This means it doesn't matter how it happens. It doesn't matter how many steps had to occur to go from your reactants to your products. It only matters that it changed from that reactant to that product. And we're going to look at reactions that occur in 1 step, 2 steps, 5 steps. And the difference is how many steps happened for the same reaction. And we're going to find out that the enthalpy change is exactly the same. So we'll observe a temperature change in the surroundings, which indicates that a reaction has occurred. And we can't measure the system's total kinetic and potential energy practically. So that's why we study the change in enthalpy. And we can do that using a technique called calorimetry. And this basically is a vessel in which you measure the temperature change of the surroundings, and your system is contained in the calorimeter and is occurring. But we're going to get to that later.